Hello and welcome back to the video course about linear algebra. Here we learn a lot about vectors, matrices and how we can solve a system of linear equations. And indeed, this is how we will continue in this new part 40. More precisely, we will talk about the so-called row echelon form. This is a special form of a matrix we will need to solve a general system of linear equations. However, before we start with that, I first want to thank all the nice people who support this channel on Steady via PayPal or by other means. In fact, now it's also possible to join the membership directly on YouTube here. And as a member, you have access to a lot of additional content like PDF versions and quizzes for all the videos. Okay, then without further ado, let's talk about the row echelon form of a matrix. So maybe you remember, in former videos I already told you that this form generalizes the upper triangular form of a matrix. However, a triangular form only makes sense for square matrices, and now this row echelon form is also applicable for rectangular matrices. And now here I immediately want to show you an example. So you see, we have a 4 times 5 matrix and a lot of zeros are involved. So you should immediately recognize this is very similar to the upper triangular form. However, for the row echelon form, the characteristic property is given by these steps here. So you should see these steps here are defined row by row and they start with each number which is not 0. Hence, for each step we have a non-vanishing number starting this step. So you see, in this example here, we have exactly 3 of these. Moreover, I can already tell you these numbers here we call pivots. And you might recall from the last video that these were exactly the numbers we needed for doing the Gaussian elimination. Hence, these are important numbers we use throughout the whole algorithm. And then at the end, what remains is this row echelon form. Okay, so now after seeing this example, I would say it's no problem to put this into a general definition. So we start with a matrix A, which is of rectangular form. Therefore, in general, we say it has m rows and n columns. And then this matrix is called to be in row echelon form if it fulfills 2 conditions. The first condition we see immediately here in the example. If there are any rows that are completely filled up with zeros, then they have to be at the bottom of the matrix. Otherwise, these nice steps here would be broken by such a 0 row. Moreover, then you also see the second condition, because we want to have a step when we go 1 row below. Therefore, for each row we have to condition that the first non-vanishing entry here has to be strictly to the right to the other non-vanishing entry. Hence, we can formulate this sentence like the first non-zero entry is strictly to the right of the first non-zero entry of the row above. And of course, first here means that we look from the left-hand side. So for each row, we start at the left and then we go to the right and see when the first entry arrives. So maybe it's helpful to look at another example again. And here now I want to take a 4 times 4 matrix. Hence you see we want this row echelon form also for square matrices. In other words, it's a very general concept here. Okay, so this is the whole matrix and now we check if we have the row echelon form. This means we start at the top and go to the bottom row by row and from the left to the right. So in the first row we see there is our first pivot. So please don't forget, we call these non-vanishing entries pivots. Okay, then let's go to the second row and then we see here, strictly to the right of the first one, we find the second pivot. And please note here, what happens to the right of the 2 here does not matter at all for our row echelon form. In other words, you can have a lot of different row echelon forms with the same pivots. Okay, then to the third row and we see the next pivot is this 3. And as before, it's also strictly to the right to the pivot above. And last but not least, you see the first condition is fulfilled because the 0 row here is at the bottom. Indeed, in a 0 row, we can't find a pivot. Therefore, for our 4 times 4 matrix here, we only have 3 pivots. However, we see we have a very nice row echelon form here. So with that, I would say now you have a good visualization for row echelon forms. And with that, we are ready to talk about 2 more very important definitions. More precisely, now I want to talk about the variables, the unknowns, that occur in a system of linear equations. Maybe just imagine we have the same matrix as above, but now with a right-hand side. For what we want to discuss here, it does not matter what the right-hand side exactly is, so I just choose some numbers. However, please keep in mind here, each row of this augmented matrix represents one linear equation with 4 variables. Indeed, we know for each column we have a different variable. And usually we would call them x1, x2 and so on. Okay, but now we want to give these variables some special names depending if pivots occur in their column or not. So first we have the variables with no pivot in their respective columns. And these we now call the free variables of the system of linear equations. Hence, in our example we see here there's only one free variable, namely x3. Because in all the other columns we find a pivot. However, they also get a special name, namely the variables are called leading variables. So they are leading and also dependent on the free variables, as we will see soon. So for our example here, this would be x1, x2 and x4. And then our goal would be to rewrite all the leading variables as functions depending on the free variables. Indeed, by doing that, we get the whole set of solutions for the system. So maybe it's very helpful to write down the whole procedure again to solve a system of linear equations. So the system is given as ax is equal to b, and then we write it as an augmented matrix. And then we apply the Gaussian elimination with the row operations to bring this into row echelon form. So now we know that the Gaussian elimination always gives us a row echelon form. Hence, at this point we are able to distinguish free and leading variables. And then what we can simply do is to bring all the free variables to the right-hand side. Therefore, on the left-hand side, what remains is what we already know, and you see it is some triangular form. In particular, there we already know what to do. We can simply do the backwards substitution to find the solution set. So in summary, you see this is what we have to do step by step to get the whole set of solutions for the system of linear equations. And I think it's worth it to look at another example to see the whole procedure with explicit numbers. However, since we have practiced the Gaussian elimination already a lot, I would say we can start the example with the row echelon form. Therefore, let's take the example from the introduction above, but now with a right-hand side. So for our example here, I want to have 3, 2, 8 and 0 on the right-hand side. Okay, and now on the left-hand side we see we have our well-known row echelon form, and also please recall the columns correspond to the variables. And we see we have 2 free variables, namely x2 and x5. There are no pivots in the 2 columns, hence by definition these 2 variables are our free variables. Okay, and now our procedure here tells us that we have to put these to the right-hand side. So therefore, let's rewrite this matrix here. So as you can see here, we want to remove the 2 columns on the left-hand side, which means we need to subtract them on both sides. For this, please recall that one row represents a linear equation with the corresponding variables. Hence, if we want to get rid of this 2 here, we have to subtract 2 times x2 on both sides. So on the right hand side we then have 3 minus 2x2. And that's it for the first row, because we don't have to do anything with x5 because it's 0 here anyway. However, not in the second row, there we have minus 4 times x5. However, we also see x2 is not involved in the second row at all. Okay, and then similarly, we subtract minus 8x5 in the third row. Okay, and then finally we see nothing changes in the last row at all because it's a zero row. In other words, the last row does not give us any information at all. However, please note that the last equation would not be satisfied if we had a non-zero element in the right corner here. In this case, the set of solutions would be empty. But in this case now, we have solutions and we can find them all. We get them simply by the backward substitution we already know how to do. However, I still think it's a good idea to write it down. Therefore, please recall, we have to start at the bottom and then we go upwards. Now, the first equation reads 4 times x4 is equal to the right hand side, which is 8 minus 8x5. Okay, now in order to keep everything clean, maybe let's give the free variables here on the right a different color. And then you see, the only thing we have to do to get x4 is to divide by 4. And then you see, we have solved the problem for x4 because only numbers and free variables are involved here. So please note, saying that x5 is a free variable means it could be any real number. And depending which real number we choose for x5, we get a different number for x4. Okay, then let's go to x3, to the next one, which means we go to the second row now. So this equation now reads 2 times x3 minus 1x4 is equal to 2 minus 4x5. Okay, at this point you know how this backward substitution works. We have to put in what we already know for x4. Hence, this gives us a new equation. Indeed, it's not so complicated, but we see the only leading variable now is x3 in this equation. And all the free variables we have to put to the right hand side again. Hence, on the right hand side we get 4 minus 6x5. So we simply divide by 2 and then we have our result for x3. So it's 2 minus 3 times the free variable x5. So you see here as well, depending on which real number we choose for x5, we get a different number for x3. And this is exactly what we want to solve our system. Okay, and now only the last row and the last variable x1 remains. However, this equation is very simple. We have x1 plus x4 is equal to 3 minus 2x2. And please don't forget, x2 is also a free variable. But x4 on the left hand side is not, therefore we have to get rid of this by using this equation here. So you see, we simply put that in and then we bring all the numbers and all the free variables to the right hand side. And then we get our result for x1, which is 1 minus 2 x2 plus 2 x5. And there we have it. This is the result we want for x1. Okay, and now to finish the whole thing, let's write down the set of solutions S. So here you should know, this has to be a set of vectors where the vectors have 5 components. However, we already know 2 of the 5 components are free variables. This means, as we already know, we could choose any real number for them. Hence, you would write that x2 and x5 come from the real number line. In other words, we have the freedom to choose these variables. Moreover, after choosing these 2 variables here, we already know the values of the leading variables. More precisely, we can replace them by a function of the free variables. Indeed, this is exactly what we will do now. This means we don't touch the free variables, but we change all the leading variables here. So first, we know x1 is given by 1 minus 2x2 plus 2x5. And then x3 is given by 2 minus 3x5. And then finally for x4 we have 2 minus 2x5. Okay, there we have it. This is the set of solutions for our system of linear equations. And to end this video, I can also tell you that we can rewrite this a little bit. Namely, we can split it up into a linear combination of vectors. So first we have the constant vector and then the part with x2. And finally, the last part would be the one with the x5 variable. So you just look, what are the coefficients for x5? So in the end, you should see this is exactly the same vector, just now written as a linear combination. We do that because then you see that the solution set is indeed an affine subspace as it should be. So in this case, you see it's a shifted two-dimensional subspace. Therefore, we would say we have a two-dimensional solution set. In particular, you see we have infinitely many solutions. Okay, I think that's good enough for today. Let's look at more abstract implications of this fact in the next video. Therefore, I really hope that I see you there and have a nice day. Bye.